6.3 Numerical Model by Bobby Moore. Numerical Model Introduction. Biomechanics is to do with the concern with internal and external forces acting on the human body, and the effects these forces produce. Kinetics is about the internal and external forces that cause the body to move the way it does. Examples of external kinetic forces are gravity, muscles, friction, and external resistance. In addition, examples of internal kinetic forces are muscle contraction, tension in ligaments, and muscle lengthening. Whereas kinematics is about how the force is dealt with. For example, if there is motion or movement, kinematics can be measured by calculating mass times acceleration. An example of this is time, speed, and mass aspects. There are also different types of kinetics, for example, linear kinetics and angular kinetics. Linear kinetics, also known as linear motion, is all about the force applied to an object or of an object, and also has two connecting motions, which are rectilinear, which is to do with the motions in straight lines commonly found on sliding surfaces, the connecting motion in curvilinear motion, which is all about the motion in a curved line, which can be seen when a ball is thrown. Angular kinetics can also be known as angular motion, which is to do with rotation, and an example of this is when a basketballer does a slam dunk. Angular motion can only occur when around an axis. Linear and angular motion can occur at the same time. For example, if somebody is in a wheelchair, then they will be using angular motion shown by their wheels, and linear motion to go forwards and backwards. Another form of motion is called projectile motion, which occurs when an object, once projected or dropped, continues in motion because of its own inertia, plus the influential force of gravity. An example of this is when a swimmer dives into the water. Linear motion. Linear motion is made up of a few aspects, and these are scalars and vectors, speed and velocity, distance and displacement, acceleration, and graphs. Scalars are to do with how big, far, or fast an object is, and has a magnitude value. Examples of scalars are distance, speed, mass, and inertia, whereas vectors are to do with how fast an object is up and down, and includes direction, for example, displacement, velocity, acceleration and deceleration, and weight and momentum. Speed is measured in meters per second and measures how fast an object or body moves. To calculate speed, you will need to divide the total distance by the total time. For example, if an athlete ran the 200-meter race at a time of 25 seconds, the average speed of the athlete will be 200 divided by 25, which is 8 meters per second. On the other hand, velocity measures how fast an object or body has moved in a certain direction. This therefore means that it is measured in meters per second plus the direction, and the calculation for velocity is total displacement divided by total time. And an example of velocity is an athlete ran 200-meter race east in 25 seconds, which would be 200 divided by 25 equals 8 meters per second east. Distance is the sum of all movements and doesn't include direction. Displacement, however, is the distance from the start to the finish of an object movement. Displacement depends on directions such as positive and negative, north, east, south, west, and angles. An example of displacement is when swimmers do a 400-meter relay race, which involves them going back and forth in a 100-meter swimming pool. When calculating displacement, in this example you will find there is no displacement, because the athlete finishes where they started and therefore hasn't travelled. On the other hand, when calculating distance, you would say the athlete travelled 400 meters. Acceleration is the rate of change in velocity. Acceleration can be calculated by dividing the change in velocity by the change in time. Graphs can be made to show visual representations when analysing an athlete's performance. As an example, I'm going to use a speed graph, which looks like this. Scenario 1 is a cyclist is training for a marathon and has decided to go out for a ride. They leave home and travel 200 meters in 50 seconds. They then stop for a drink for 100 seconds. The athlete then decides to do another 300 meters before going home. This takes them 200 seconds. The athlete then takes another 200 seconds to get home. On the graph, we can see that the lines have different gradients, which represents the speed at which the cyclist is going. To calculate the speed of a cyclist, you will need to split the graph into sections and find the time, distance, and divide them. Force. Force is strength or energy as an attribute of physical action or movement. Force also has many effects on an object, which are rest to motion, change in direction, acceleration, decelerate, and change in shape. Rest to motion is all about an object going from no movement to movement, whether it is little or big. An example of this is when a tennis player throws the ball up in the air to serve. This is because the ball starts off with no motion in the player's hand, and then gains motion from when thrown in the air, because there is then gravitational force, and the ball has the force from the hand. Change in direction is also another effect of force, and this is all about an object essentially being stopped by a force and pushing into a different direction. An example of this is when a tennis player returns a serve. Force can also cause acceleration to occur, for example, when a tennis player hits the ball or when a basketballer throws the ball. Deceleration, on the other hand, is the opposite and is about how we use force to stop or slow down an object. For example, when a basketballer catches a ball, they apply force in order to slow it down. Change shape is about force being applied to the objects, forcing them to change shape. An example of this is when a squash ball hits the wall or tennis racket and flattens on the contacted side. However, it then changes back to shape when no force is applied. Newton was a great physicist who came up with 3 laws to do with force. His first law was called inertia, which was all about how the object won't stop moving unless another force is applied to it. Newton stated that every object persists in its state of rest or uniform motion in a straight line unless it is compelled to change that state by forces impressed on it. An example of this would be when a basketball player throws the ball, because unless the basketball hits a wall, backboard, person, hoop, or even the resultant force from the ground. However, Newton's second law is all about the resultant force. It's all about more acceleration or force is needed to move a heavier object than it is for a lighter object. An example of this would be when a performer goes into the gym and starts lifting weights. They will need more muscle or force to lift heavier weights. Newton stated that force is equal to the change of momentum per change in time. For a constant mass, force equals mass times acceleration. Newton's third and final law stated that for every action there is an equal and opposite reaction. It is all about how forces come in pairs. For example, in basketball, when a player is dribbling the ball, Newton's third law is being shown. For the ball to bounce up again, there had to have been an equal and opposite force to push the ball back up again. Force can cause different types of motion, which are rotary motion is turning around in a circle, such as a wheel turning. Linear motion is moving in a straight line, such as a 100-meter sprint. Finally, reciprocating motion is moving backwards and forwards in a straight line, just like a 400-meter relay race or even the butterfly stroke in swimming. Direction force and eccentric force are 2 types of forces. That a force whose line of action which does not pass through the body's centre of mass is called an eccentric force and results in movement and rotation, whereas direct force is when force is applied to the centre of the body or object, resulting in it moving forward in a straight line. An An impulse is another way of describing force. However, an impulse is about how long a force is applied to an object or body. It also relates to change in momentum that occurs as a consequence. A calculation of an impulse is force times time. An example of an impulse is rowing, because the impulses come from each stroke made by the oars when they exert the boat forward. Momentum is a tendency for a moving object to keep moving once it's in motion. Momentum is also the amount of motion possessed by a moving object and is the product of mass and velocity. An example of this is when a basketballer throws the ball, and therefore the mass of the ball is 0.25 kilograms times the velocity of the ball, which equals momentum. Stability and instability. Stability is the position of the centre of gravity. This means that the lower the centre of gravity, the more stable an object becomes. However, most people consider stability to be at its highest when there is a wider base of support, which is true. For example, a basketball player will have their knees shoulder width apart and bent with one foot slightly in front of the other when performing a box out, ensuring that they are stable enough for when the opponent tries to attack or defend. Although we naturally like feeling stable, instability is key in most sports and is considered an important part. For example, diving. When a diver wants to jump forwards off the board, they go up onto their tiptoes, decreasing stability, slightly lean forward, forcing their centre of mass in front of their body, causing them to go forward instead of straight up. Stability is also about where your centre of mass is, because if your centre of mass is not in the centre of view, but is forward or backward, you are likely to fall over. As I said in the example about a diver will want to move their centre of mass forward in order to dive forwards without bending. A line of gravity should be going through the middle of your body towards the centre of the earth. An object or person is said to be unstable when the line of gravity is outside the base of support, which is why when the base of support is larger, it is more stable because it takes longer for the line of gravity to fall out the area. Data can be collected many ways. However, the two main ways for it to be recorded or measured. Recording is to do with whether or not it is taken in a 2D or 3D dimension. 2D setup can be done in many ways, and there are certain factors that should be taken into consideration. For example, the angle it is being taken from, which can cause the parallax error. If it is facing up, it can give a different result as to when it may be facing up. How close you are to an object you are filming, which can also cause an error, which is called the perspective error, which is to do with if you are filming someone jumping and you are too close, you will only catch half the jump, and therefore won't catch the whole thing, which will change the result. The whole body shots are important as well. If the camera you are taking the recording on is manually focused, you will need to make sure it's been set. If the shutter speed is on slow or not on motion, then it will only catch certain aspects of the performance. It can also let less light in when taking shots. The final part of the camera setup is the frame speed. For example, the more frames there are per second, the better the recording when taking motion shots. 3D imaging is to do with Vicon. When measuring, however, there are other errors. For example, perspective error, which is to do with the perpendicular aspect of the camera to the object. Horizontal scaling is to do with the whole movement done in different planes of motion, can be hard to capture because of the positioning of the camera in 2D. It is easier in 3D when measuring the jump. We could have made the participant hold a ruler to their side at the beginning to allow the software to measure the jump. In this slide, you can see that on the left is data taken from a student who did a vertical jump and reached a height of 0.27 meters. Whereas when a professional athlete does this test, they get a higher jump because they are more bodily equipped to jump that high and are used to it. Howard was able to produce around 1,210 pounds of force to push himself up into the air and produce 1,506 watts of power.